Our next application of integration is arc length. Now by arc length, what we mean is this. Suppose we have a curve, some curve specified by a function, and suppose the function is continuous, no holes, no jumps, no vertical asymptotes. It is differentiable, so there are no cusps. Remember, sometimes we have issues with cusps, but we have no holes, no jumps, no vertical asymptotes, no cusps. So this is what we actually call the definition of that would be a smooth curve. And the question is, what is the distance from here to here? Imagine this, imagine we take an ant, and an ant walks on the board and does this entire curve distance. The question is, how far would that be? Or if I took a measuring tape and laid it out very carefully along this smooth curve, what would be the length of that arc that's formed from this point to the other? Arc length. The way we do this is we partition the x-axis. If we partition the x-axis, and then each one of these partition points determines a single point. I'm not going to make rectangles, just make points on the curve. Just the points on the curve. And then connect them with straight lines. Now, if I had my ant just walk on the red straight lines, that would be an approximation. Or if I laid the tape on the straight line portions only, that would be an approximation of the total length. It's just not a particularly good approximation because there's error here, there's error here, there's error here. Right? But I could make the approximation better by taking a refined partition. Now, if I refine this partition, take more of these segments and make them shorter. And then what you eventually would get is something like this, where I would have this curve, and we would have a large number of very short segments, and there might be a slight amount of error here. And so to the unaided eye, it would almost look exact. Well, as long as we take the number of those segments, they get more and more of them, but they're shorter and shorter, the approximation gets better and better. And if we take the limit as the number of those goes to infinity, then that's actually what we define to be the arc length of that segment. Now, to get from here to there to show actually the computation takes a lot of algebra that I'm going to gloss over. It actually is presented in the text in a very clear and very straightforward way. But what we can say is this. Typically S is used for arc length. S is used for arc length for reasons that come later in the curriculum. But we're going to use S to represent the arc length. S is it's the arc length letter. It's the arc length letter. Yes, S is the arc length letter. You probably are too young to get that joke. All right, so what is that? It turns out if you do a boatload of algebra, the arc length is approximately equal to the sum of all these. It's 1, well, let's see, how do I want to write this? 1 plus f prime of x quantity squared delta x. Where this comes from is a boatload of algebra and some factoring that's kind of weird, and it actually stems from the distance formula. The distance formula is given by delta x squared plus delta y squared, and you can see this kind of arises from that. But for our purposes, it suffices to say this. The arc length is given by the following. If the curve is given by y is equal to f of x, then the arc length is the integral from a to b, the endpoints of the partition. It's just the endpoints of the partition. It's the square root of 1 plus the derivative quantity squared. That's the formula for arc length. All you need is the formula for arc length. You do not need to develop it. You do not need to see where it comes from. Just know that if you're given a function in this context, that's the formula for finding arc length. All right? Now, So all we need now is to do a few specific examples. Suppose our f of x is given by sine of 2x, and we're on the interval from 0 to 2 pi. So let's draw a rough sketch of that picture. You don't necessarily even need the picture, but for the record, I think this is it. Here's 1, so there's pi, there's 2 pi. We have to go through one cycle. We have to go through another cycle. So very roughly, that's the picture. We want to find the arc length of that entire curve over the interval from 0 to 2 pi. Okay. And all we need is endpoints of the partition, 1 plus, I need the derivative. So we do need to find the derivative chain rule. So this is 2 times cosine 2x. And so we can construct this. The arc length is given by the integral from 0 to 2 pi. I need the square root of 1. It's always 1. This 1 arises from the algebra that led us to this formula in the first place that we're going to forego discussion of. And then I need the derivative. So this is 2 cosine 2x, quantity squared, square root of the whole thing, dx, and you're out. All I'm going to ask of you is to set up the integral, which finds, set up an integral which finds that arc length. Square root 1 plus derivative squared, integral from the endpoints of the partition.